Hello everybody and welcome again to the ice-breaking of the class of Advanced Hydrosystem Engineering. Today we will see together the uniform and permanent motion in pressurized conduits. In particular, we will define what is a uniform and permanent motion. We will compute and evaluate the resistance laws for distributed losses. We will talk about some practical formulas for water mains, and we will compute concentrated losses. So finally we will be able to write the hydraulic system equation for an hydraulic plant. Let's start with the definition of uniform and permanent motion in pressurized pipes. Basically, a uniform motion is a condition where the values and distribution of velocity are contemporarily the same in each section along the motion of your flow. The volumetric discharge remains constant along the conduit, but can be in this case time dependent, which means that basically your volumetric discharge can change along the time, but it's the same for each section. In the case that we are considering, for example, a turbulent motion, we consider the average velocity. If the motion is also permanent, then the dependence on time is negligible and the volumetric discharge is totally independent from time, so is constant in space and time. So, what happens inside a cylindric conduit? Consider, for example, that we are in front of a uniform motion. Basically, it means that your hydraulic gradient J is equal to your piezometric gradient. Remember that I was minus the derivative of the of H, so the piezometric head, over the space, while J was the derivative minus the derivative of the total head over your space. Then you are able to define tau zero, which is called the tangential tension, as the specific weight of your flow times R, which we will define the next, times J. J, integrate along a definite space, is called again the hydraulic gradient and is given by the total head in section number 1, for example in this section right here, minus the total head in section number 2, over L, which is the distance between the 2 points that you are considering. So basically, J is the slope of a line that link the total head in section number 1 to the total head in section number 2. In the same time, R is defined as the hydraulic radius. The hydraulic radius is the ratio among the cross-section area that your flow is encountering during its motion over the wet perimeter. So, for example, let's try to define it graphically. And let's try to not make any disaster. Alright. So, basically, suppose that you have a circular pipe then the cross-section area, so this is the front of your pipe, then the cross-section area is exactly what is inside the pipe occupied by the flow. So suppose that your flow occupies the entire area. This is the cross-section area, while the wet perimeter is defined as the perimeter which is in contact with your flow. So it's this one. Then, for example, let's try to compute the hydraulic radius for a circular pipe. Then we'll have that R is given by A over the wet perimeter, but for example in this case A is equal to the cross-section area, so it will be pi. Suppose that we have this R0, so the radius of your circular pipe is given by R0, so we will have pi times R0 to the power of 2, which is the area, over the wet perimeter, that is exactly this part, so it will be 2 pi R0. Then simplifying, you get R0 over 2. Since usually the characteristic length of the pi is defined as the diameter, so the diameter will be 2R0, this comes to be d over 4. In the same way you can define all the hydraulic radius for all the kind of geometry. So for example, suppose that we have a geometry like a rectangular one, so we'll have that this side is A while this one is B. Again, we won't define the hydraulic radius, so we will have the hydraulic radius given by A over B. In this case, A is this area, while B again is the perimeter in contact with your flow, so it's this area right here. So we get that the area, of course, is A times B, while the perimeter would be 2A plus 2B, or AB over 2 that multiplies A plus B. In the case that, and sometimes it happens if you're talking about open channel or large river, sometimes it happens that your A, which is the length of your cross-section area, is much higher than its width. So basically this dimension A is really much higher than B. Then it follows that in this stuff right here that we get, if A is really higher than B, then this term comes to be almost equal to A. So for this particular case we get that AB is over 2A. Then simplifying, it's B over 2. And this is the hydraulic radius for a rectangular section, while this is the hydraulic radius again for a rectangular section where your length right here is really higher than this dimension. Alright. Okay, so let's go back to our slide. So we get exactly here I reported what we have just right now demonstrated. And let's go on. So again, our aim is to define the distributed and concentrated losses that a flow encounters during its motion. To do this, you have to first distinguish what kind of losses you want to define. Second one, remember that everything is regulated by two main things, which are the nature of your flow and the geometry of the section that is encountering. So, in 1883, Reynolds conducted an experiment to define three different kinds of flow. Basically, he put a stain inside a tank full of other liquid like water, and he gradually increased the volumetric discharge of this stain, so basically it increases the velocity of the stain. He observed that for small velocity, the stain remains almost constant, so you don't have any kind of turbulence between the stain and the other flow. So there wasn't any mass exchanges among adjacent threads, and this was typical the case that described the condition of laminar flow. Right now, it increases the volumetric discharge, so again it increases the velocity, and he observed that they started to exchange some masses between the different threads, so the adjacent threads become unstable if the velocity increases. In this case, transverse velocities and mass exchange occur, and this was the condition of transition flow. Finally, he increased again the velocity of the stain, and he observed that for higher velocity, the stain totally dissolved in fluid mass, and the transverse velocities became irrelevant. So this was the case described by the turbulent flow.